Okay, next one. Oh, number 8. Number 8. On page 352. A chemist reacts 50 mils of 4.5 molar carbonic acid with excess potassium hydroxide. How many grams of potassium carbonate are produced? Let's see. Start out with 500 mils of a 4.5 molar carbonic acid, H2CO3, which incidentally is what gives Coke Fizz. 5.4 molar H2CO3. And I want to know how many grams of potassium carbonate are produced. So it reacts H2CO3 with potassium hydroxide. Potassium hydroxide. Is that right? Potassium hydroxide. And they want to know how many grams of potassium carbonate are going to be produced. Oh man, this is confusing. Where do we go from here? Well, the very first thing we got to do is figure out what's going on here. All right, we got to write the chemical formula, and not only write, but we got to balance it. Well, they told us what it's going to make. It's going to make potassium carbonate, right? But we would have known that, right? We know that that's an acid, all right? They call it, but we know it's an acid because it's got a hydrogen out front, and they also called it. Did they call it an acid? What do they actually call it here? They call it carbonic acid. So they told it was an acid. Reacting with potassium hydroxide, we know potassium hydroxide is a base because there's OH in it. All right, so it's going to form, we know, water and a salt. Right, so here's our water, and we got to figure out what this salt is going to be. All right, so what's the salt going to be? Well, it's going to be carbonate plus potassium. But what is that going to look like? It's going to be potassium and CO3. Right, that would be a good guess. A better guess is you have to keep in mind what these two ions' charges are, right? Remember when we did, way back when, we did something like calcium Cl2? Where do we know, why is that a 2 there? In order for this to remain uncharged, to remain neutrally charged, we know that it's all got to balance out. What's the oxidation state of calcium? Well, if you look in your periodic table, the oxidation state is in the second column. Oxidation state of calcium is Ca2+. What's the oxidation state of chlorine? Negative, right? So we've got a +2 here, a -1 here. We know that I'm going to have 2 negative chlorides to balance out this 1 +2 calcium ion. Right? And I showed you that shortcut where you assume this to be 1 and you move this up here and you move that up there. Remember that? To show you where these numbers came from. Right? So this 2 dropped down here and this -1 drops down here and you end up with CaCl2. Well, what we need to do is take a look at what this potassium carbonate ion looks like. Carbonate ion, if you look on page 288 of Apologia, shows you the oxidation state of this polyatomic ion. And the oxidation state of the polyatomic ion is 2-, -2. Right? So we know what's the oxidation state of potassium? Potassium is in column 1. Its oxidation state is +1. So what do you think is going to happen here? Remember the shortcut. This 2 moves down here. This 1 moves down here. And we end up with something that looks like K2CO3. Right? Now it's all balanced. I needed 2 potassiums to balance out this CO3 is -2 charge. And you know, you didn't have to look on page 288 in your book to see that carbonate was actually CO3 2 minus. You could have looked right here. How does H2CO3 tell you the oxidation state of this polyatomic ion? Ah, yeah, because there's a 2 down here, right? I have 2 hydrogen. What's the oxidation state of hydrogen? Hydrogen's a +1, right? So I have to have 2 hydrogens here for some reason. Why would I have to have 2 hydrogens here? Because this CO3-2, this charge on this is actually -2. This 2 came from this, right? This one down here came from the hydrogen. You don't see there's a 1, but there's actually a 1 here, right? Yeah, I hope that makes sense to you. So we know that this actually had to be CO3-2 minus because of this 2 on the hydrogen, right? If this were actually HCO3, what would you anticipate the charge on the polyatomic ion CO3 to be? Well, I would anticipate that then to be -1, right? Because there's only 1 hydrogen. If there were 3 hydrogens here, what would you anticipate the charge of the carbonate ion being there? Well, it would have to be 3. Right? Because these 3 hydrogens, all with a +1 charge, have to balance that out. Wow, now that I made that clear as mud, let's go ahead and take a look. Let me rewrite the formula since I really kind of messed things up. Oh, heck, I'll just rewrite the whole thing. Alright, so what was it again? Hold on, let me write it down. It was H2CO3 plus KOH reacts to form potassium carbonate plus H2O. And I hope I'm going to jump back here and make sure I got that all in my... That's a little messed up. Let me put up something. There we go. Okay. Alright. Good. Okay, so is this balanced? Oh, probably not. No, I can see it's not balanced immediately because I got 1 potassium over here, I got 2 potassiums over there. Alright, potassium is the odd bird here, so let's go ahead and balance for potassium. Stick 2 in there. How does that look? Now what do I got? I got 2 hydrogens here. I got 4 hydrogens over here, right? 1, 2, 3, 4, right? This 2 comes to here, so I got 2 times 1 hydrogens, 2 hydrogens. I got 4 hydrogens over here. Only got 2 hydrogens over here. I got 5 oxygens over here. I've only got 4 over here, but look, all I just got to do is do this. I just saw it 2. Stick a 2 in front of my hydrogen. All right, so now I've got a total of 4 hydrogens over there. I got a total of 4 hydrogens over here. I got a total of 5 oxygens over here. I've got a total of 5 oxygens over here. That's balanced. Well, that was an easy one. All right. Now, what are we going to do with this? Well, what kind of information did they give us? They gave us this 4.5 molar. 4.5, what's another way to say 4.5 molar? 4.5 molar is the same thing as saying 4.5 moles per liter. Uh-oh, moles. Moles. Uh-oh, we got moles. That's telling us that it's going to be a mole-to-mole ratio. Somewhere in here it's going to be a mole-to-mole ratio. Why, we knew it was going to be a mole-to-mole ratio because it's asking us if I have a bunch of this, if I have some of this, how much of this am I going to make? So I've got to somehow turn this, the carbonic acid, into potassium carbonate. it's a mole-to-mole ratio. When it says I've got 20 grams of this, how many grams of that can I make? Right, I got 20 grams of A, how many grams of B can I make? Whenever I turn something from A to B, from one substance to another substance, it's got to be a mole-to-mole ratio. That's the only way in chemistry you can do that. That's why the mole-to-mole ratio is so hugely important in chemistry. All right, so I have this 4.5 moles per liter of H2CO3. Now, whenever you do a mole-to-mole ratio, I've always told you to start out with what you know. What did they give you? Well, they gave us, what did they give us? I don't know. What did they give us? They gave us a chemist reacts 50 milliliters, 50 milliliters, 500 milliliters, 50 milliliters of this. With that, how much of this am I going to make? Well, I used 50 mils. That's what they've given me, right? It's just like when we did mole-to-mole ratios using molar mass, we start out with how many grams, right? If I give you, in that last problem, when they gave us like, I think it was 450 grams of sodium hydroxide, how many moles is that, right? Well, you start out with what you're given. We're given 50 mils, right? 50 mils is 1, 2, 3, 0.05 liters. It's got to be in liters, so it's 0.05 liters of H2CO3, right? Liters cancel, boom, boom. Now what do we want to do? Well, we've got it in moles. If we have it in moles of H2CO3, what's our next step? It's in moles. The very next step is we run it home doing the mole-to-mole ratio, right? We can go with how many moles. We're going to do moles of H2CO3 on the bottom, right? Because that's going to cancel with these moles. And what moles are we going to turn it into? Yes, magically we're going to turn this into moles of what? Moles of potassium carbonate. How many moles? What's the ratio? Well, this, how many moles of H2CO3? Well, this is 1, right? There's a 1 here. There's also a 1 out here, right? So it's 1 mole of H2CO3 is equal to 1 mole of K2CO3. So 1 mole of this reacts to form 1 mole of this. 1 mole of this reacts to form 1 mole of that. Right? That's what our balanced equation does for us. If we didn't have a balanced equation, we couldn't do this mole-to-mole ratio. Right? For this equation, this mole-to-mole ratio is correct. But what does it ask us for? It wants us to how many grams of potassium carbonate are produced? Well, it's in moles of potassium carbonate now. Everything else canceled. Liters are gone. Liters are gone. Sure, this is liters of C2CO3, right? All that's gone. Right now, our answer is just sitting in moles of K2CO3. How can we figure out how many grams of K2CO3 there are in that many moles? I mean, that's a simple thing. We're just going to go 1 mole. One mole of K2CO3 is equal to how many grams of K2CO3? We got to use our periodic table and calculate how many grams of K2CO3 there are in 1 mole, and that's 138.2. 138.2 grams. You plug and chug all that out, and you should end up with 32 grams of K2CO3. Where did we get this number? I hope nobody asked that. But if someone did ask that, we got that number by figuring out what each of these components weigh. What is potassium weigh? One potassium atom weighs 39 grams. 39. What does 1 carbon weigh? 12. What does 3 oxygen weigh? 16 times 3. 16 times 3 plus 12 plus 2 times 40 or 39 is equal to 138.2. 138.2. And that's where that answer came from. Oh, that is so simple, Mr. Mike. That's cool stuff. I really like it. Let's do another. Are you sure? Okay, we'll do another.